So I'd like to introduce Dawei Mu at the National Center for Supercomputing Applications. And he's going to talk a little bit about their tool for doing data conversions and aggregating HDF5 files.
So, morning, everyone. My name is Dawei Mu. I am the system engineer of NCSA. I serving in the innovative system lab. Today, the topic of this presentation is tar2h5, a small file packer for machine learning tasks. First, please allow me to use some time to introduce our system. Our system named HAL, which is a NSF-funded IBM cluster for deep learning applications. This system composed of 16 compute nodes, 640 physical CPU cores, and 64 NVIDIA V100 GPU, as well as 224 terabytes of all-flash storage. The origin of the machine name is based on a classic sci-fi movie, 2001: A Space Odyssey. In this movie, the HAL is a computer that evolved with artificial intelligence and start to killing everybody inside the movie. So it doesn't end well, and we decide to revive this and give him a second chance. This system has a few highlights. One of them is using the IBM Power 9 CPU. I used the red color highlighted the key point. First is that this CPU have SMT, a very strong thread performance, which it supports SMT4, which means it has 40 physical cores per node, but when it maps to OS, it will be 160 CPU, the logical CPU. And it also supported NVLink 2.0, which make sure the connectivity between CPU and GPU and the GPU to GPU. This is also the very early generation of machines that support the PCIe Gen 4. Which is also ensures that the bandwidth between CPU and CPU memory to GPU memory are fast for data transfer. The power source of this machine, of course, is the NVIDIA V100 GPUs. It has a 7.8 teraflops double precision for peak performance and the 15 teraflops for single precision. One highlight, since it has PCIe Gen 4 and also the NVLink 2, the memory bandwidth of the GPU memory is up to 900 gigabytes per second. And as for the storage, we are using the DDN GS400 NVE all-flash array server. This storage system have 224 terabytes of usable GPFS with 8 EDR InfiniBand connection, which support a theoretical of 100 gigabytes per second bandwidth. The mean time to list all home directories has been 7 milliseconds, with a standard deviation of just 17.8%. The HAL system, we're using CentOS Linux 7.7. The compiler includes the GNU 4.8.5. advanced toolchain version 12, the IBM Excel, the CUDA, and the PGI compiler. The tools, the machine learning toolsets, we mainly use the Power AI 1.7.0, which changed the name to Washington Machine Learning Community Edition. We also have Open MPI for internal communication, and the CMake for automatic build and compile, as well as the Singularity as our container solution. Okay, so this is the introduction of our system. And now let's talk about the I/O challenge of our system. First is, let's talk about the data set, which is known as the catalyst of the rise of this wave of machine learning. Now we can, our user researchers can gathering millions of pictures, videos, tests from internet. So it's getting more and more easy for users to getting data sets to the internet, and those and the access pattern of this data set when they doing the training job is dominant with random access. The researcher who new to this area, which is I will say dominant amount of users on our system, they are from the domain science, which means they have their expertise in their own domain science, but they don't have a lot of HPC experience. So they intuitively just using small files as data sets rather than large packet single file. So these way of training their models produce a overwhelming workload to our shared storage. I mean, before we purchased this all NVMe flash storage system, we used to use a spinning disk as NFS throughout these compute nodes, and the performance was so bad that we have to reduce the working compute node to ease the I/O pressure. So that's why we start to thinking of how should we provide a proper tools for our users. We are very lucky to collaborate with HDF5, especially thanks for Gert Herber for his help. That we just discussed the need of the user, and we start to develop this tar2h5 small file packer. This software simply converts the tape archive to HDF5 files. The rule of thumb is we want this tool to be very easy to use for our new researcher on this system. Also, we want this tools can be used for solutions for different scenarios. The functions we packed within this toolkit, including our archive checker, our H5 compactor packer, and the H5 shredder packer. The archive checker is used for our user to check how many files actually within the archive and how many files are larger than 64 KB, which could be which could use our if the file is all smaller than 64K, we can use a compactor packer. If the file is larger than 64K, we have a shredder compactor for this type of data. The H5 compactor. The H5 compactor converts the input tar file to HDF5 file. All the files within the tar file should be smaller than 64 KB, using the file name as the dataset name. The picture I insert within this slide is a demo for it's a demo case for the usage of the tar2h5. As we can see, all the picture I choose is copyright-free picture, and the theme is coffee. Since this business is a coffee like boosted business, yes, so the original file name will be the dataset name. So it's very easy for user to get the information about the data about the data set they are reading. And another solution for smaller for a small file less than 64K is the H5 compactor SHA1, which as we can see, I'm using exactly the same demo dataset, and this compactor SHA1 converts the input tar files into HDF5, just like the compactor, but all the file within the tar file will use the files SHA1 digest as the dataset name. So that using this is that for those datasets that the file name doesn't need let's say have any meanings within their training. So we can save a certain amount of storage. As well, this has another benefit that since we're using SH1 as the file as the dataset name, this compactor will automatically eliminate all the redundant small files within the dataset, which is it's an extra bonus. And then for the files that is larger than 64 KB, we have a H5 shredder which converts the input tar files into HDF5. For this one, we do not have any file set limitation. We have concatenate file names, the offset, and its data into 4 separate array for our random access, which is also shown within this image. We have the image with save all the image raw data, and the image offset indicate it's saving the start point of this certain image. The same rules apply to the name and the name offset. So we developed this case. We developed this tool basically, when we having a use case, which I'm going to show in this slide, is that even though after we switch to all-flash NVMe drive, this system is also cannot sustain with a very overwhelming workload from storage system. I mean, even the hardware is amazing, but it still have its limitation. At that time, our storage system started to showing the severe reduce of performance due to many of the training jobs that within this research group, that which they are using the GAN as the model to doing training for efficient large scale video generation. So the user is from SC Research. It's a computer science department, the research assistant Daniel McKee. His data set is a large kinetic 400 video data set, which composed of around 240K videos. So during the training, he will using certain intervals to have a snapshot of the video. So the number of the file of a single data set is around 25 million. And this is just a portion of its data. And the total size, at that time, the total size of the GPG dataset is around 125 gigabytes of worth of data as a tar file. So at that time, when they are training the model, they actually untar the file and create more than 25 million of the small files and read directly from our storage system, which cause it's a very it's a very heavy workload for our storage system, especially considering if you run multiple of them. So after we have this two sets ready, and we help them to convert this 125 gigabyte tar file into a 125 gigabytes of HDF5 files. They did not need to change they didn't change their code too much, just a few liners, but the loading performance has greatly improved. The loading from the compact, because they are using very small, like around 16 to 32 kilobyte JPEG files. They are using compactor, the compactor packer. So so after we convert this tar file into the compact HDF5 files, they're training the overall training performance is about 5 times faster. And also we can, since using this HDF5 solution, which greatly ease the pressure of our storage system, so our system can serve many users at the same time, or load a similar job, load multiple similar jobs without any pressure. The tar2h5 file is already open source under the HDF group official GitHub repository, and we have all the source code and using CMake to perform the automatic building process, And there's a demo case already loaded yes. And also we have a very detailed installation and usage instruction attached within the README file. And as for the visualization, we recommend to use the newly developed HDFCompass, which is also used for all the snapshots for this presentation. As about the future work, we will continue collaborate with HDF5 group, focusing on the direction to the mixed precision support. So we are looking at the traditional FP16 and the Google bfloat 16, as well as the latest NVIDIA TensorFloat 32, which is just announced along with the unpaired generation of GPU, and also the AMD FP24. So that's pretty much of all my presentation. Thank you very much for your time.
Thank you, Dawei. We have probably time for maybe one question, and then people can talk in the chat window if they have further follow-ups.
Okay.
Any questions for Dawei? Okay. And then we'll transition to, thank you, Dawei.